Okay, so in the previous video, Anna gave you a nice introduction and overview of locality-sensitive hashing. In this video, I want to talk about some motivation and give two concrete examples. So let's begin. So what is our motivation here? We'll talk about that. That's going to be to an algorithmic speed up of near neighbor searching. So we're going to say, let's write it down again. And then we'll give two examples. The first example will be apply an application to curves. And the second will be to persistence diagrams. So we'll call these PDs from now on. And Robin gave a nice talk about them on Wednesday. So hopefully we all saw that talk and you have some idea of what that is. Okay, cool. So how can this be beneficial? Well, say you want to do a near neighbor search. So what do we have? So we have a set of objects. I believe Anna called these documents, but I'll keep them more general as objects. Have set of objects. So P is something, some objects, and let's say we have N of them. And then we have Q as a query object. And we want to find the element of P that is closest to Q. So find the PI in P with the distance between PI and Q is minimized over all PI. So we want to find the nearest neighbor essentially. So hopefully that makes sense. Okay. So algorithmically, what are we going to do? Well, one thing you could do, the naive approach, is just iterate over P and compare, compute the distance to Q for each element and return the closest one. So we could do brute force. And that's going to give us big O and the size of P. So we have to iterate over that to compare everything to get a value. So this is where we're going to see some improvement. So we can do better. We can find a near neighbor or approximate. So we sacrifice a little bit. It's an approximation algorithm, but in many applications, that's okay. All right, so what is our first application? So this is a paper by Dremel and Silvestri from 2017. And we have Anna introduced a lot of variables. So we have to, what are those variables in this context? So here an object is a polygonal curve in RD. So think about your GPS trajectories as you walk around. Here's a nice path in R2 as an example of that. So how do we compute? We need a distance. So how do we compute the distance between two curves? Here we're going to use the Fauché distance. There's other distances. And intuitively, we have let's look at two curves here that are pretty similar. So let's say that's C1 and this is C2. So we want to know what is the distance and the Fauché distance from C1 to C2. Intuitively, you can think of a dog on one curve. So that's a dog, and a person on another curve, and they're connected by a leash. And we want to know what is the shortest leash we could possibly use so that they both can walk forward. So maybe the dog would walk the whole way to the end first, and then the person walks. And so we would need a leash this long. But that's longer than the minimum. So we want to minimize this maximum. So let's get rid of that. And so a better strategy would be they traverse the curves simultaneously. And then our maximum would be maybe that. So we're going to take the minimum of a max leash. And that'll give us, that's a nice distance. The paper also considers the dynamic time warping distance, but we won't get into that here in this video. Okay, so we have objects. We have a way to compare them. And now we need a hash. So here our hash in both examples is going to be snap rounding. So we place grid over our space, and then we move our points to the nearest intersection. And snap points to nearest intersection. So that'll give us a nice hash function. So let's look at some pictures. So let's say we have this grid, and let's look at a curve. So maybe my first curve looks something like this. And we could say, okay, if we hash this thing, so if we do hash C1, what are we going to get? Well, we're going to say, okay, here's your closest grid point, here's your closest grid point, and here's yours. And so we'll get this curve, and we can represent this as a vector. So this is 1, 8, 3, if you like. And so we'll hash it to that value. And then to relate back to Anna's video, we have this property that gives us locality sensitive hash. So if we have two curves, let's draw another one, just hopefully we don't get too cluttered. So let's say we have another curve. And its Fauché distance, so this is C2, is really close to that of C1. Well, then you're going to hash to the same thing. And if the Fauché distance is really big, so let's see one of those, maybe a curve that looks something like this. So this is C3, h of C3, what would we get? A different vector, we'd get like 7, 2, 6. So that is certainly not 1, 8, 3. So we get the required properties to be a locality sensitive hash. So that's pretty neato. Oh, I want to say, how does this help? Let's add a page. So how does this help with our speed up near neighbors? So speed up searching. So we can do hash O of P, hash P. So this is still O of P, but this is only one time. When we did it before, maybe I didn't say this, this is OP per query. So each time you would query, you would have to do OP. But here we just do it once to hash, and then we hash P, or hash Q, pardon me. And then we look at elements of P that are in the same bucket, and those are our near neighbors. So this is constant time, so look in bucket. How am I doing on time? Find neighbors. And we can refine this grid. So maybe you could chop it up more, you know, and then you'd get fewer neighbors. And so if you're interested in a lot of near neighbors, you could do a coarse grid, and a unique near neighbor, you could do a fine grid. Okay, so we get some speed up. The paper, it's now going to be logarithmic. There's some other parameters as well, but I don't speak too broadly, but in general, you get a linear to logarithmic speed up, which is pretty cool. Okay, for the second example, we have a local connection. Our professor was one of the authors. Also, Brittany Fazy and Bin-Hai Zhu are on this paper, and Sam Mika, who graduated last year with a PhD, was also on this paper with a few of Bin-Hai's collaborators as well. So they wrote this paper. So what are our objects? Here our objects are persistence diagrams, so PDs. So what do they look like? We have a diagonal, and then we have some points off the diagonal. We need a distance. So here we're going to use the bottleneck distance. And so let's say, what are we doing here? Same idea as curves. We're going to minimize some maximum. So if one of my persistence diagram are these blue X's and one of these, let's say, red circles, the bottleneck distance is we're going to connect the points and try to minimize the maximum distance that any point would have to move. So this would be our distance realized by these 2 points here. If we tried, maybe, you know, you could match this to this one, but that's not minimum, so that's not going to be our bottleneck distance. Oh, but with this matching to the diagonal, it makes things more difficult. So the diagonal is hard to deal with, so the paper goes through and tells you how to deal with that. And then what's our hash going to be? It's going to be the same thing. We snap rounding again. So we place a grid if we have a diagram. We could place a grid over top. And then we could snap to whichever intersection point our point is closest to. And we would get the same sort of result we had here. Maybe we'll just copy this down since it's so similar. But instead of the Frechet distance, now we're using the bottleneck distance. And we see we have all the requirements to be a locality sensitive hash here. Okay, so just to recap, what do we got? We got motivation. You can speed up near neighbor searching. And 2 examples. One is where we're dealing with curves in RD. And the second one is persistence diagrams. Okay, hope you liked it. Bye-bye.